Welcome. So we are going to be continuing our discussion now of improper integrals, and in particular we are going to be addressing the function of deciding whether or not an improper integral converges without actually needing to compute exactly the value of the integral. So we'll start with this example here, the integral from 1 to infinity of 1 over x to the fifth plus 1 dx. And from last time, we know that this is equal to the limit as b goes to infinity of the integral from 1 to b of 1 over x to the fifth plus 1. So the problem here is that last time we were able to actually compute this definite integral from 1 to b exactly, and then we were able to take the limit as b goes to infinity. And in this particular case, we don't have a good way of anti-differentiating 1 over x to the fifth plus 1. So that's where comparison comes into play. So if you go to the link at the bottom of your handout here, you'll get to a Desmos worksheet where I have a graph of the function 1 over x to the fifth plus 1. And so if we just kind of zoom in over the region we're integrating, we can look and we can see some properties of this function. By the way, I've put here in green some code for shading in line 3, shading the area under the curve. So you can see I'm shading points x, y, where x is greater than y is greater than 0 but less than f of x. And also I only want to shade where x is greater than 1, since I'm taking the integral from 1 to infinity. And so we can see that it looks at least plausible that this function might have finite area, the shaded area, but we don't know until we actually take a limit, and the problem is that we can't take that limit that we would like to be able to take. So some of you had asked the question, how do I just look at a graph and know whether it converges or not? And the answer is you really can't. So sometimes you can kind of look at a graph and you know that if your function doesn't even go towards 0 and you're taking the integral from 1 to infinity, then there's no way it could converge. So you can sometimes see something, but generally you can't tell unless there's another function plotted where you do understand the behavior. So let me go ahead and plot the function, a related function. So we'll just plot the function g of x (1 over x to the fifth). Whoops, something happened there. (1 over x to the fifth). There we go. Okay, so it turns out that we actually do know something about the convergence of 1 over x to the fifth, and we know that actually this function f of x looks an awful lot like g of x. So we suspect then that our function f of x has a convergent improper integral. So let me just record that here. Note that 1 over x to the fifth plus 1 looks like 1 over x to the fifth, at least for large x, and the integral from 1 to infinity of 1 over x to the fifth dx converges. So we suspect that 1 over x to the fifth plus 1, the integral from 1 to infinity, converges too. Okay, so that's our suspicion. And we'd like to be able to make that rigorous. And so the way to do that is to notice the following. to confirm our conjectures, what we want to do is we want to use the fact that 1 over x to the fifth actually converges, combined with the fact, and I didn't point it out very clearly the first time we looked at these functions, but we want to combine that with the very important fact that actually everywhere along the interval that we are integrating over, 1 over x to the fifth plus 1 lies below 1 over x to the fifth. So if I zoom in here far enough at any point, if you zoom in far enough, you'll see that g of x is above f of x here. And that holds anywhere along this graph. As I go out further, they get closer together. Okay, but I could zoom in a little bit more and I would still see that g of x is larger than f of x. So, okay, let me pinch out a little bit so we can look at what's happening. So if we know that there's finite area under the larger curve, then the smaller curve certainly has less area, so there's still finite area under the smaller curve. So that's the punchline. Okay, so consider that we know, so we know that x to the fifth plus 1 is always greater than x to the fifth. So 1 over x to the fifth plus 1 is always less than 1 over x to the fifth. Hence, we know that the integral from 1 to b of 1 over x to the fifth plus 1 dx has to be less than the integral, and I'm going to go ahead and just be safe here, less than or equal to the integral 1 over, from 1 to b of 1 over x to the fifth dx. So if I took the limit, then the limit 1 over b, 1 over x to the fifth plus 1 dx. If I take the limit, then I get the integral from 1 to infinity. Has to be less than or equal to the integral from 1 to infinity of 1 over x to the fifth dx, and we know that that 1 over x to the fifth, that integral converges. So we know there's a finite area. Right. So the idea then is that the improper integral of the original function must also have finite area. So this is known as the comparison principle for improper integrals, and I've stated it on the next page. And so there are two parts to this comparison test. So the first part is we need to guess whether or not our interval converges or not. In the last case, in the last example, we guessed that our interval converged. So if our interval converges, then what we need to find is we needed to find in that case, find g of x that satisfies this inequality here, so we need to find a g of x that's bigger than our f of x and which converges. And if that's the case, then we know that the integral from a to infinity of f of x, our function, also converges. On the other hand, if we are in a situation where we are guessing that our function does not converge, right, then we need to find a g of x so that g of x is less than our function and it diverges. Right? And so let me go ahead and give a little cartoon of that one. So in the case where where we have some function f of x and we think it diverges, so we want to show that f of x diverges, then we need to find g of x. So we need to find some g of x so that this area and let's say that this is a here. So we need to find some g of x that is greater than f of x so that we need to find that g of x is greater than f of x and g of x, the integral diverges. And if that's the case, then we will be able to conclude that the integral from a to infinity of f of x dx also diverges. Let me go ahead and just put the cartoon up here for your notes of the first case. So if you wish to show that f of x converges, right? So you have your function here, f of x, right? And you want to show that the integral from a to infinity is finite, then what you need to find is you need to find a g of x. So you need to find a g of x so that there's finite area under g of x, and then if f of x is below that, there must be even less area under f of x. So these are the two pictures here that I think are good to keep in mind when you're thinking about the comparison test here. So why do you think that we need the function to be positive? In this case, we want to avoid the potential issue of our graph maybe oscillating. Also, if our functions are always positive, then all of the areas are always positive, so we never have to worry about an infinite negative signed area. So it is actually very important, let me just comment here, that it is really important that we always have zero being a lower bound for all of these functions. Okay, so let me go ahead and give a version of the comparison test for the other kind of impropriety. So here, if we have say a vertical asymptote at and I'm going to go ahead and assume that the vertical asymptote is at x equals a, and we're integrating from a to b. And so I'm going to go ahead and actually just draw the cartoon of what happens here. So if we have a and b here, right, and I have a function f of x, okay, and then I'm going to go ahead and draw another function here. Okay, and I'm just going to maybe redraw my function here so that it's a little more believable that my function is having the behavior I'm kind of claiming it should. Okay, so here's my two cases here, and if we, all right, so case one, we wish to show that that the integral diverges. So I guess what I should be saying up here, we're not really saying whether or not f of x converges. We're trying to say that the integral of f of x converges. So let me just add an integral sign here. So suppose we want to show that the integral of f of x dx from a to b converges. So what do we need to show? We need to find, in that case, we need to find a g of x so that zero is less than or equal to f of x less than or equal to g of x. So in this case, we need to find a g of x that's above f of x where there's finite area. So the corresponding integral from a to b of g of x dx converges. Sometimes we kind of abbreviate converges by writing less than infinity. So let me just go ahead here and put, here's my g of x, and this area here is finite. Okay, and then let me go ahead and draw the corresponding picture for the other scenario. If you wish to show that the integral from a to b of f of x dx diverges, so in other words, there's infinite amount of area, then what you need to find a g of x so that a positive g of x that's less than or equal to f of x everywhere on the interval we care about, and so that the integral from a to b of g of x dx is infinite. So there's infinite amount of area under the purple curve here. And so if we did find such a g of x, then that would imply that f of x also has infinite area. Okay, so I want to note it. I want to, maybe before I move on, I should point out that if you have, it really is important that your function has the same, exactly satisfies these properties, right? So in particular, if I'm trying to show that a function converges, I'm always needing to compare with a function whose integral also converges. And if I'm trying to show convergence, the comparison function, so the g of x, has to always be bigger than the function that I'm investigating. Otherwise, being if g of x here is not always above my f of x, then I can't always make the claim that the integral under f of x is less than the integral under g of x. So it really is important that you have all both of the conditions in the statement here have to be satisfied. You need to have the first thing is my single star here. You need to have g of x being greater than f of x, and the second criteria here, you need your g of x to actually be convergent. In the same way, you have two criteria for divergence, right? You need to have a g of x that's always less than your f of x, and you need to have the area under your g of x being infinite. So that's just, I just want to highlight that all of those things are important when you apply these rules. And then last time you computed some integrals for some families of functions. And so I just want to go ahead and make sure you have the right answers for these. And it turns out that these are very, very useful for comparison functions. So good functions to have in your hip pocket to really understand their behavior, because that will allow you to do a lot of, to make conclusions about a wide range of other functions. So I just want to point out here, and I'll just summarize what you should have gotten for answers. In the first case, we're looking at the improper integral from 1 to infinity here of x to the p. So we have it that it converges for p greater than 1, and it diverges for p less than 1. And if we're taking the integral from 0 to 1, that's also an improper integral, this is going to converge for p less than 1, and it's going to diverge for p greater than or equal to 1. And I apologize, up here this should also be diverges for p less than or equal to 1 in the first family. Notice that for p equals 1, we have divergence on both of these integrals. So the function 1 over x is a badly behaved function, or has a divergent improper integral on both of these regions here. And then the function that I have listed here, this exponential, is going to converge for all a greater than 0. Okay, so now it's time for your turn. So what I'd like for you to do is to consider the following example. Decide which comparison is useful in determining the convergence, and then apply the comparison test. Okay, and when we pick up, we will discuss your responses.